guests and for gathering us here to have this public lecture under the theme, Next Frontiers for Artificial Intelligence, from Health to Renewable Energy and Sustainable Alloy Design and Recycling. We thank you for the gift of our resource personnel, Professor WOLE. We thank you for all the efforts, all the researches and the impact into health, energy, and sustainable materials for the humanity and for the world. We pray you, O Lord, entrusting him into your care. Use him to treat us to this topic so that we will all be inspired to think through and be able to contribute our efforts to this development. We are grateful to you for the planning committee and for making this day a reality for us. Be with us, direct us, and steer the affairs of everything that is happening here to the greater glory of your name. These and many blessings we ask through Christ our Lord. Amen.
Reverend Father Fatana, thank you so much for the open prayer. So we're going to the introduction of the chairperson. And today our chairperson is no other person but our Vice Chancellor, Professor Mrs. Rita Akusia-Dixon. A round of applause for her. Well, Professor Mrs. Akusia-Dixon attended St. Monica's Secondary School in Mamponashanti, where she studied for her GCU ordinary level examination and later Wesley Girls High School in Cape Coast for her GCE advanced level examinations. Now, she graduated from the Kwame Nkrumah University of Science and Technology with a bachelor's degree in pharmacy in 1994 and acquired an M.Pharm in the same university in pharmacognosy in 1999. Now, she received a PhD in pharmacology from King's College London in 2007. Now, Professor Dixon began a career as a lecturer at the Kwame Nkrumah University of Science and Technology in the year 2000. After leaving to pursue further studies in the UK, she returned to Ghana in 2007 and continued lecturing at the Kwame Nkrumah University of Science and Technology. And in 2009, she was promoted to senior lecturer and further to associate professor in 2014. And in September 2018, she was appointed the Pro-Vice Chancellor of KNUST, making her the first female to occupy that position. Now, prior to her appointment as Pro-Vice Chancellor, she was the Dean of the Faculty of Pharmacy and Pharmaceutical Sciences. Now, Prof. Dixon currently serves as the Board Chair of the Pharmacy Council of the Pharmaceutical Society of Ghana, and on June 2020, KNUST announced her appointment as the first female Vice Chancellor of the university. And also, she works as a phytochemist and covers areas of bioactive natural products in the management of communicable and non-communicable diseases. Shall we welcome the Vice Chancellor of the Kwame Nkrumah University of Science and Technology and also the chairperson of this occasion, Professor Mrs. Rita Akusia-Dixon.
Thank you very much, Kwesi. When he was carrying on with the introduction, I was asking myself, am I the one to give the lecture? So I'm glad that I'm supposed to chair, which is very easy to do. So I thank you all for your cooperation, which I believe we can all get this afternoon. As I say, good afternoon to all of you. As I give our students the time to quickly settle in, and then we can take off. A warm welcome to all of you. And I'd like to recognize especially our guests. So Professor WOLE Soboyejo, President of State University of New York, Sony Polytechnic Institute, and all the very strong, powerful delegation that came with him. Once again, I recognize you, and I welcome you to the best university. Registrar of the University, Finance Officer, Provost, Deans and Directors, Project Lead, KNUST Engineering Education Project, KEEP, Professor J.J. Ponyo. Of course, we have the Provost here. Once I've mentioned KEEP leadership, I will have to also say the Provost, who is Professor Kwabena Brichum Nyako, Provost of Engineering. I recognize you. All members of convocation, distinguished ladies and gentlemen, staff, my dear students, friends from the media, a very good afternoon to all of you once again. I said good afternoon to all of you, please. Thank you very much. Let me start by welcoming our distinguished guest and, of course, our scholar and our lecturer this afternoon. Prof, we are very delighted that you made time to take on this lecture, and as a university, we are grateful for your time. As we all say in our local dialect, we say akwaba to you. And I guess by now you are beginning to understand what that language means. I want to hope that you're enjoying the hospitality of the Ghanaian people, and specifically that of the Kwame Nkrumah University of Science and Technology. We are excited that you'll be focusing this afternoon on next frontiers for artificial intelligence, from health to renewable energy and sustainable alloy design recycling. Indeed, as a professional pharmacist myself, the aspect of AI that relates to health obviously excites me. And not just in health, these days, I guess there is nothing that you will be able to talk about without introducing this topic, artificial intelligence. It has come to stay. And earlier we all accepted that and created the environment where we can take advantage of the opportunities associated with AI, the better. And not just take advantage of the opportunities. Anytime you see opportunity, challenges are just next door. We also need to look at what are some of the challenges that we need to deal with, and especially when we talk about the challenges associated with AI, we cannot forget the ethical implications. To be able to respect and create that culture of awareness and create an environment that is conducive for especially you, the young people, to be able to think even in the space of artificial intelligence. I am proud of the fact that the Kwame Nkrumah University of Science and Technology, through the Responsible Artificial Intelligence Lab, and watch that word, responsible. If we put responsible in front of AI, then we will be safe. As soon as we leave it, we are in trouble. And we are very lucky to have a whole lab led by Professor Ponyo, who leads this for us in the university. And we are happy with the partnership that we share with our friends. I am extremely delighted that the Sony Polytechnic Institute has taken time to spend so much time with us. They were with me at the council chamber meeting management this morning. I've spent a lot of time at the College of Engineering, and interestingly, for some time now, we have had a memorandum of understanding with them, and all the conversations that we have had today arrows the fact that the future of our partnership can only look bright as we look forward to solving problems in our societies and improving the quality of life of the people that we serve. Thank you very much once again, Prof, for this friendship that your institute is sharing with KNUST. We can assure you that we are very committed to this call and we will continue to do our very best as we travel with you on this journey. And we also want to invite you and the team that you make the Kwame Nkrumah University of Science and Technology your second university, Ghana your second home, so that even beyond this partnership, anytime you want to take a holiday, can you add Ghana to your list? Can you do that for us? Thank you, thank you. We are looking forward to this initiative and this collaboration being able to train the critical minds that we have. And let me say that we have over 80,000 brilliant ideas and minds here at the Kwame Nkrumah University of Science and Technology who are all ready to change their worlds positively. My students, I thought you would clap for this. Oh, that's not you. Am I talking about you? I'm not a lecturer this afternoon, so let me just finish and go and sit down. As we look forward to an exciting and thought-provoking lecture this afternoon, let us keep in mind that AI is just not about advanced algorithms or machine learning models and so on and so forth. It is also about human beings. It's about researchers, engineers, innovators, policymakers working together to turn visions into realities. And as I said earlier, to solve problems as we all ensure that humanity, the life of every human being, is improved in our communities. And on that note, once again, I welcome all of you, and especially Professor WOLE and team, and we're looking forward to a very exciting interaction this afternoon. I thank you all very much. Thank you.
Another round of applause for her. So for such an august occasion, we equally need an august group to pamper our ears. So we have Ejako, Nimo, and Adadamu Agofoma to give us the musical interlude. A round of applause for him. Another round of applause for them. Thank you, Ajakwinimu and Adadamu Agrofoma for that beautiful music. So, gradually, we're going to the crux of the matter. And we're going to do the introduction of the speaker, and it will be delivered by the Provost of the College of Engineering, Professor Kwabena Brichum Nyako. Let's welcome him.
Good afternoon to you all once again. I'm delighted to introduce our speaker, and our speaker is Professor Winston WOLE Soboyejo. He is a Nigerian-American material scientist and engineer. He is currently the president of the SUNY Poly, that is State University of New York Polytechnic Institute. He is a Nigerian American because he was born in California at a time when his dad was studying for his PhD at Stanford University. From Stanford, the family moved to Nigeria. So Professor WOLE went back to Nigeria, and he grew up at the campus of University of Lagos. Between 1997 and 1982, he was sent to a boarding school in Nigeria. Before proceeding to King's College, London, 1982 to 1985, where he received his BSc in mechanical engineering. I think our Vice Chancellor also went to King's College. So they are talking about King's College. After his BSc in mechanical engineering, he went on to Cambridge University, where he received his PhD in material science and metallurgy. So from Lagos to UK for his bachelor's and then Cambridge, and then he said, okay, let me go to America because I am also American. So he moved to the United States to work as a research scientist for McDonnell Douglas Research Labs. That's 1988 to 1992. He was also a principal research engineer at the Edison Welding Institute. That's 1992, before joining the engineering faculty at the Ohio State University, 1992 to 1999. Professor WOLE was a visiting Martin Luther King professor at MIT, 1997-1998, before moving to Princeton University between 1999 to 2016. Professor WOLE is one of the founders of the African University of Science and Technology and the Nelson Mandela Institute of Science and Technology. He also served as a president of the African University of Science and Technology from 2012 to 2014. He was also Dean of Engineering 2016 to 2018 and Provost 2018 to 2022 and Interim President 2022 to 2023 at the Worcester Polytechnic Institute in Boston. Professor WOLE was also elected to the U.S. National Academy of Engineering in 2021. I thought you would clap to it. He is also a member of the World Academy of Science, the African Academy of Science, the Nigerian Academy of Science, and the Nigerian Academy of Engineering. Professor WOLE served on the Scientific Advisory Board of the UN Secretary General between 2014 to 2017. He was also one of the consultants that assisted the World Bank in preparing the background document that led to the African Center of Excellence. And we are happy that KNUST has 3 of such centers: KEEP, RESC, and TREK. So, audience, this is our speaker for this afternoon, Professor WOLE Soboyejo.
Okay. Prof. Is it? Have a seat. Please sit down.
Thank you so much, Provost Nyako, Vice Chancellor, distinguished ladies and gentlemen. I have to say I feel very humbled being in this great hall for the second time in my life, giving a talk from this spot. I think just over 20 years ago, I was here with the great Professor Andam to give a talk in which I really reflected on what science and technology can do for Africa. And what I'd like to do today is to build on that theme, especially in this era of the 4th Industrial Revolution, the era of artificial intelligence, and think about what science and technology can do for all people in ways that can address problems of health, problems of energy, and problems of how we turn our resources into wealth in ways that we can drive, especially at a place like KNUST, where we have 80 to 90,000 talented scientists, technologists, humanists, who in my mind can really change the world. And as we think about this, I want to start by not just acknowledging all the dignitaries, but really acknowledging all the students, all the faculty, all the staff, all the collaborators that have made what I have to talk about today possible. And I list only some of the names because I recognize that whatever you achieve is really due to those that work with you and team with you. So, as was said in the introduction, I started work in the US, working for a major corporation and doing work that I thought was important. And one day, my mother asked me, she said, "Wole, what are you working on?" So I said, "I'm working on hypersonic aircraft. They can do all sorts of things and morph. And in fact, they're very sexy." And she said, "How sexy are they?" I said, "They're really sexy." And then she said, "What difference does this make to the lives of people?" I couldn't answer her. "Oh, it makes the aircraft go faster. So what?" "What difference does it make to the lives?" Then she added, "Our people." So having grown up in Africa, I grew up in an environment where I knew people didn't have basic things like water and access to health and energy and basic things. And at that point, I knew I had to change what I had to do. So I went off to MIT for a year, hoping to discover this. I found complicated professors doing things that were even more complicated. And I realized that that was not my path. And in looking into myself, I then started a journey that took me first to South Africa, where there was a convening of US and African scientists to think about what we could do to address our challenges. And that happened at the Farm Inn. And as I started to think about this, I made sure that I wrote down all the problems people described, and I convened them into teams that worked on them. And what you're going to see today is the outcome of that thinking. From farming to today, what we have basically been able to do by collaborating with many Africans and doing many things with American scientists that believe in the same cause. So the first thing to realize in this game is that it's all about teamwork and finding problems that matter. So if you look at the problems that matter, those problems in many ways represent local challenges or global challenges. So problems of energy are global, but they're also local. And what you need to do is to find the demand-driven aspects of these problems and then tackle them with teams that can really profit from them. I say this because it's not only about doing good, it's about finding solutions that people will pay for and use in ways that get applied in communities across the world. It's also about defining those problems around the science and the purpose. So for example, if you look at our challenges in health and you ask the question, what are the biggest killers of people in Africa? Actually, the biggest killer of people in Africa is cardiovascular disease. What's the second biggest killer of people? It's cancer. And by the year 2030, cancer will overtake cardiovascular disease as the leading killer of people. So 30% of all death cardiovascular disease, 20% of all death, 22% cancer, racing towards 30. And it's a major problem. And so the question is, how do we address that in ways that can use new science, new nanotechnology, and perhaps AI to enable us to detect cancer and treat cancer? We have challenges in water purification, and the pipes are broken between the water production areas and the tap. How do we purify water at the point of use in a way that removes bacteria, viruses, and chemical contaminants? How do we make the solar cells of tomorrow? And how do we develop the affordable housing and infrastructure that our people can use based on our own materials and based on our own science? So at this point, what I did, and this happened around 2000, was to bring groups of people together to work in interdisciplinary collaborations where I wasn't necessarily the expert, but we had a goal, and we were lucky enough to convince people to support us. And what happens actually is you really then get into a framework of continuous learning where students drive you, all sorts of visiting scholars drive you. And I can tell you, I actually have a few Ghanaians from KNUST in my lab, such as Tabiri and Elvis Chumesi, who drive me to the point where I communicate with them at 2 or 3 a.m. in the morning as we pursue these different activities. So, so within this context, we now live in a world of machine learning, and we find that that world of machine learning and AI is so pervasive, and it allows us to do so much in learning, in discovery. It allows us to do so much even in the creative arts that it's really very striking to see and begin to think of what this really means for us. Now, when you look, for example, at this example of self-driving cars, in many ways it inspires what I'm trying to present to you. So you see here an example of a self-driving car that's interacting with its environment, sensing the positions of various obstacles, navigating its way through, being able to detect objects, obey street signs, identify where to stop, interpret weather conditions, and make all of these decisions using cutting-edge sensing artificial intelligence as it exists today. So the question is, can we take this kind of capability and extend it into our work on developing the energy solutions of tomorrow, developing the health solutions of tomorrow, and perhaps giving value to the materials that we have. And so this is what has inspired our efforts. And we've been encouraged by the fact that this is not only inspired science and technology, it's inspired virtual assistants that can help with speech recognition, all sorts of ways of interpreting text and parameters and text response that are ubiquitous around us today. Next, please. And going beyond that, even in the arts, with generative AI, we can interpret texts and draw things and do things with continuity. And so the question then is, how do we go from this to the next frontiers in the solutions that we're trying to pursue? Next, please. So as we think about this, I want you to imagine the following scenario. In one case, I want to spray on a surface the structure of a solar cell with the organization of elements into layers in ways that I can optimize even before I do the experiments. In another case, I want to develop ways of detecting cancer in Africans whose forms of cancer molecularly are not always the same as those of other people from various parts of the world. And as I think about this, next please, I want to take the old traditions of the Africans who made bronze and brass, who figured out how to use those elements to make alloys that created all sorts of instruments that created earlier African civilizations. And I want to connect that to the latest tools in alloy design today, such that we can use those same elements that are here in Africa and create new alloys with incredible properties that have never been achieved until now. And I want to do this with a group that is here. But actually the key thinking that led to much of the applications we see today came from Albert Einstein's work on the photoelectric effect. And he basically recognized that you could absorb photons and excite electrons into higher conducting states. And that, plus then subsequent development of materials that could enable this to happen, really took a major leap, especially with the development of silicon, and led to ultimately the applications of these in light-emitting devices and solar cells. The problem, though, with silicon is that this technology is expensive to introduce into a manufacturing environment. And so if you want to manufacture silicon solar cells, you need a plant that costs at least $100 million. So most people cannot play in that space. You also need clean room environments that are expensive to maintain. But if you now move forward to today, there's a new class of solar cell materials known as perovskite solar cells that you can make simply from solution processing, and you can develop into platforms for commercialization based on your ideas and your access to data. And so what we're doing is to explore these possibilities by asking some scientific questions. And so one of these scientific questions is, what are the limits in terms of efficiency of these kind of systems? The theory, the Shockley-Quasar theory, tells you that the limits in terms of efficiency are about 30%. On the other hand, if you can really play with machine learning models, you can use those machine learning models along with the understanding of the physics to really ask the question, can we exceed those theoretical limits or approach them? And can we design new systems that have efficiencies close to those 30% suggested by these materials? Now, to get to this and to have a unique advantage, there's a little trick that I learned. And this was a trick that I learned when I was playing with light-emitting devices which can be thought of as solar cells in reverse. Now, with light-emitting devices, I had a colleague called Stephen Forrest, who is a pioneer in that industry. And he was trying to solve a problem where he was wanting to stamp LED pixels onto a substrate. And so him and I figured out that you always have impurities at the interfaces. And when you apply pressure, you can create contacts that enable the cold welding of those thin films. And also, those contacts improve charge and light transport in ways that improve device performance. And so we had a patent that was issued for this about 10, 15 years ago. And I really didn't understand why Steve wanted to patent this thing until eventually this was licensed by Samsung in a process that's used to make organic LED screens. And so till today, I get royalty payments that I never expected to get through this discovery of this process. And so there's no reason you cannot apply this to solar cells and other devices. So this pressure application and stamping method, I've chosen to apply to a number of opportunities to make solar cells, light-emitting devices. And in some of our early work, what we found is that if you apply just the right amount of pressure, you increase the efficiencies a lot. If you apply too much pressure, the impurities begin to damage the device. And so the trick is to know what is right in terms of pressure application. And if you actually look at the materials that you're applying pressure to, what you find is you can take digital images of those materials, and as you start forming cracks that degrade the device. And once you have that understanding, you can now use this as a method to significantly increase your efficiencies well over what you can get just by doing chemistry alone. So with all things, what we always try to do is develop a physical model. And so we can say, well, if you understand the physics of the contacts and you solve the contact mechanics problem, you can work out your contact length versus your available length in a way that tells you how much of the surface you have in contact to allow charge and electrons to flow through the layers. So with this idea, we were able to make solar cells with efficiencies of 23%, which is well above that of conventional silicon solar cells. We're able to relate also the contacts to simulations of the contact, and ultimately we did modeling and simulations to understand those contacts. What happens if the impurity is soft in between? What happens if the impurity is hard? What happens if the impurity is somewhere in between? Next, please. And as you do those works, the computations begin to help you understand what's going on in terms of how these soft, hard, and intermediate contacts limit or enable the contacts. What came out of that work is that you have to have very soft materials at the top to improve your contacts during manufacturing. Next, please. Okay, and you can actually show that during the contacts, the materials become amorphous. All sorts of things happen to promote the contacts. Next. In ways that produce not only solar cells that are as good or better than silicon solar cells, but those solar cells last without degrading for about 6 months. Now, our goal is to make solar cells that last 35 years, which means that with this kind of an approach, you can now begin to say, well, we can begin to imagine some competitions that might work. Next. Now, at the end of the day, what is the connection to AI? So, if you have images like this of the surfaces, those show the different defects that are present as you apply pressure as these devices degrade. What you can do is digitize these images, and using machine vision, you create descriptions of these images that are digital. And then using machine learning, you can, please move on, you can essentially learn the images that are associated with different degradation states. And with computer vision algorithms, you can automate the defect analysis And you can use convolutional neural networks to facilitate then the detection and segmentation in ways that allow you to characterize different states with these approaches. And so with these, you can then begin to learn the associated images and also predict different states associated with the evolution of life in these structures. So with methods like this, you can now begin to play with machine learning guided experimental strategies in which you relate those defect states and use them for continuous improvement of the processing parameters associated with the fabrication conditions. And if you have a KNUST professor like Elvis Tumasi visiting your lab, you can become even more ambitious. And so Elvis shows up, and I say, you know, Elvis, we've been getting all this data, and we're trying to really improve on what we have done. So he said, but you know, there's a global database that has all the data that's been collected in the world that's any good. Why don't we search that space and then use machine learning to understand that information in ways that could enable us to identify perhaps even better compositions that could achieve more than what's been achieved before. And so we started this journey by basically looking at those databases, analyzing them, and trying to see what we can learn. And we also collaborate with someone who's really an expert in how you treat or pre-treat the data to enable you to really get the best out of the modeling of the available data. Her name is Rodika Nyamtu. So here's the data from much of what's been collected in the world that has been really validated to be good. And out of this, what you realize is that in the case of just regular regression, if you compare the predicted data on the y-axis to the actual data on the x-axis, what you find is that the regression approach doesn't work. And what you find is that something called the random forest approach really characterizes the variabilities in the data for all of these systems. And if you look at the error analysis, this also bears this out for much of the data, that with the random forest approach, we can characterize these variabilities for all the possible compositions of perovskite that have been studied and reported on. Next. And you can now say, what about if I vary my electron transport layer or my hole transport layer? How sensitive are my predictions to these? And what you begin to find is you can now start identifying composition ranges that take you to efficiencies of 22.5 and even some that take you to efficiencies closer to 30. So Elvis wanted to include the efficiency of 30 in this presentation, and I told him that's not a good idea. But the truth is, we have achieved more in 1 or 2 weeks of his work than we have achieved in 25 years of effort, in terms of identifying what are the compositional spaces we can play in to really have the impact that we want to have. And I can now say, what if we now add pressure to these compositional variations? And the truth is, when we add pressure to these compositional variations, we increase our potential to achieve solar cells of even greater efficiencies than we have today. Now, what are the implications of this? So if I now say that on average we can make a solar cell with an efficiency of 10%, and we cover an area of 22,000 square miles with that solar cell, that would provide enough energy for all of the United States. And by the way, even if we think about the needs of people in rural areas who just want basic lighting, what it basically means is that we can provide solar lanterns and light for every person in Africa. And so this is important that we do this, and it's also important that we do the research in collaboration with the global community, so we are part of the ownership of this. And so really the next step is for us to start using this to inform what we do in terms of research, in terms of projects, in a way that will now allow us to begin to probe into different spaces as we use approaches like this to guide our efforts. And so the fact that you can do this in solar cells and LEDs also led me to conclude you should be able to do this in batteries. And so if you take lithium-ion batteries and you make the layered structures for these lithium-ion batteries, where you have the appropriate anodes and cathodes, and in our case we use a solid-state electrolyte of LLZO that has the advantage of being not so flammable as liquid electrolytes. And what you really want to do is to create contacts that enable the percolation pathways for ion transport and charge transport across those three layered structures. And as you apply pressure to those, what you find is that their efficiencies improve. But with machine learning approaches, what you can now do is think about how you can build on that understanding. So those contacts induce stress, which is what you see with these heat maps that we can simulate. And those stresses also ultimately lead to cracking. Next, please. And the cracking ultimately degrades the devices. So you need just the right amount of pressure. And if you apply too much, the cracks propagate, and as they propagate, the devices get degraded. And ultimately, what you can show is that the changes in impedance, next please, are related to the degradation of the devices. But you can also use databases that are global to search the compositional spaces that allow you to identify the appropriate machine learning approaches for characterizing these types of things. So not only do we have the opportunities to make solar cells, we can make batteries. And by the way, those batteries prepare us for a new world in which, next please, in which essentially we can identify the best statistical models that characterize the variations and minimize the errors. Next, we can also essentially start thinking, how does this prepare us for a world of electronic vehicles in which lithium-ion batteries and other kinds of batteries are going to be needed to meet the global demand. And in this area, I would argue that the car has essentially become a structural battery. So I hope that that gives you a flavor of what we can do in the energy field. And I want to move on now and talk a little bit about breast cancer. So in the case of breast cancer, it accounts for 30% of all cancers in women. And the biggest problems are early detection and treatment. And there are many methods, of course, that people use, but without the appropriate facilities for processing data and gathering information, it's difficult to detect the cancers early, which often means that there's not much we can do if the cancer is detected late. And it's also interesting to know that many of the drugs that were developed to target cancer in Caucasian women do not target cancer well in many African women. And so what it basically points to is the need for us to do research collaboratively that enables us to develop the solutions to these problems. So one of the potential approaches that we can take is to take little blood samples from people with a needle. So with a needle, if you aspirate out the blood, it contains cells that have different features with them. And so those features, for example, could be the radius of the cell, the perimeter of the cell. It could be the smoothness of the cell, concavity or convexity of the cell. And it could be fractal dimensions of the cell or even the texture. And so from optical images of those cells that you can digitize, you can calculate all these parameters in ways then that can enter a database. And so the most reliable database in this is called the Wisconsin database, that has thousands and thousands of data for many, many people that have been obtained over time. And this is available such that anyone can access this with the right registration. So when you begin to collect this data, what you can then do is you can do machine learning on the data, and then you start comparing the outcomes from that machine learning to a validation database that you set aside for this kind of work. And so with these approaches, we've identified different statistical models that characterize what we see. We've tested them, and these include the naive Bayesian, logistic regression, support vector machines, and these kinds of models. And those give you on average about 97% ability to detect. You can also work on immunohistochemical stained images, such as the ones shown here, where you do deep learning on those IC staining images. But you see, when you get the data in the literature, the data has different levels of resolution. And so you need a multi-resolution pool of images to do machine learning with. When you do deep learning with the multi-resolution imaging approach, you can actually then improve your ability to detect up to about 99.7% accuracy. And so if you go to the next slide, you see some of these results where we have the baseline models being considered. Next. And if you go to the case where you have this bag of multi-resolution convolutional features, your prediction accuracy goes to 99.7%. So these are all methods that we can apply. We can extend them. We can use transfer learning to expand these databases to our own African context. And I'm sure that as we do these kind of things, we improve our ability to detect with accuracy cancer, and we adopt those databases to our own environment. Next, please. And as we do this, one of the things that I realized was that we needed to get to African hospitals. And so we started doing collaborations with the National Hospital in Abuja, where we had access to human breast cancer tissue. And so with these human breast cancer tissues, we started studying them with IHC staining of different kinds and trying to classify the breast cancers. So normal tissues, you see that everything is intact. When you get to grade 1 tissues, that structure in normal starts breaking down. For grade 2 cancer, it breaks down even more. And for grade 3 cancer, it breaks down even more. So these images, even without doing any detailed analysis, you can see, enable you to detect the stages. And so we're working on the classification with automated methods. We're also trying to ask the question, what are the receptors that are overexpressed in African women? Because you see, in many cases, HER2 receptors are not overexpressed, which means that drugs that target HER2 receptors are really not effective. And so what we've identified when you actually examine those tissue extracts from African women is they overexpress different receptors, such as LHRH, luteinizing hormone, releasing hormone, ephrin A2 receptors, in ways that we can target with our drug design. The levels of expression also increase with stage, which basically means that we can start thinking about ways of targeting those cancers by designing new drugs or new nanoparticles that target those receptors that are revealed in these kinds of ways. And as you do this kind of work, you can now start thinking, next please, of new ways of imaging breast cancer, where you essentially create nanoparticles that are conjugated to LHRH or EphA2 that then target the regions with the tumors in ways that enrich the MRI images. And you can go one step further, next please, and start developing the drugs where you take whatever cancer drug it is that you have, and you start conjugating onto that the LHRH target or the EphA2 target that targets those overexpressed receptors that you find in African women. So if you go next, please. So in doing this work, what we have done is to start playing with drugs. We conjugate those drugs to those receptors that are identified. And we've done experiments, for example, in animals, where we look at the shrinkage of an initial tumor that's induced by the administration of that drug. And so if you go to the next image, what you see is that in yellow, if you have no drugs, the cancer just grows. But in green and in turquoise blue, when you have the targeted drugs, we can shrink a 1 centimeter tumor to 0 in 2 weeks. So with methods like this, as we begin to use these methods of studying the biology on the surfaces of our own cancer tissues, what we can do is really begin to do targeted medicine that allows us to create targeted drugs, that also allows us to now also connect to the hospitals to really do ethical human trials to validate whether or not to use these things. Now, 1 or 2 people have approached me and said, can we start using these in people today? And I said, no, we can't until we do the clinical work. And why is this? In my mind, whatever we do in this area has to be ethical. But what we really hope in another few years is that this will be a story of our collaboration with African scientists in a way that enables us to come up with targeted medication for our own people. In the last part of our work, I want to describe how you develop the new alloys of tomorrow. So here I know I'm in the middle of Ashanti land, and Ashanti are famous for gold. And what I also know is that there is several hundreds of years of creative work going on in local places to create all sorts of gold alloys in a way that has been important over many, many hundreds of years of civilization. Now, beyond that though, the world came about with different ways of making different alloys that have all sorts of properties. And what I'm going to describe to you today is the opportunity for us to catch up in 1 or 2 years. So it turns out most alloys have small amount of a second element added to a dominant first element. But there's a new generation of materials known as high entropy alloys, where instead of adding a little bit of one, you add equal amounts of 3 or 4 elements. Now, when you do that, you create materials with high entropy, and those materials with high entropy also have amazing strengths and mechanical properties. And typically, the way we study those is to look at how the defects in those materials evolve and give rise to strength. So you see those little micropillars. Those are micropillars designed to study the evolution of compositions and see how they deform. So what actually determines the strength of those materials is the defects you have within them and how you grow those defects. And so if we deform these materials, you see that those defects grow. We can also do molecular dynamic simulations of those defects and see how they evolve when you subject them to loads in ways that allow us to predict their strengths. And so with ideas like this, we can begin to simulate the properties of materials, right? Next, please. And so as I go through and I start doing these simulations, you need big computers, you need lots of computation, and for each alloy, it's a major effort to do the simulation. Next, please. So at the end of the day, next, please. What I can now do is to say, well, am I simulating enough of these defects? So until now, we didn't have the computational capacity to simulate that, but today we can, and this is work in collaboration with Professor Nima Rabah and Mobin Vandadi and Tabiri, where we try to say, can we simulate the defects and how they give rise to strength? Next. Next, please. So ultimately, with these kinds of things, you can predict the stress-strain behavior. The important thing to realize is at some stress, the material will yield, and that's a good measure. And at some condition of stretch, the material will fail. Next. And this is very complicated to do for every material. Next. So let's think about a simpler way, and this is work with Chumesi. And so what we said was this: if there is a global database that has all of the data that's reliable, that's being collected in the world, why don't we go into that database and apply a machine learning model to these elements? And it turns out there are 16 to 18 elements in all of those alloys. And so let's see what we can learn about those compositions and how they give rise to their properties of strength, ductility, and modulus, etc. And see if we can simplify this. And to be honest with you, it's a bit of an ambitious goal because they're collected from labs all across the world. And if you should go to the next result. Next, please. Next, please. Please move it up forward. Here we go. So this is what happens when you show all that data. It turns out that all that data collapses onto one predictive model. So what it basically means is, with this, whether you're talking about the strength of the material, whether you're talking about the ductility of the material, they're captured by the random forest model that characterizes the distributions that you can use to predict their properties. And if you notice, we can predict the hardness of the materials, we can predict the strength of the material. They're all scattered around that line, that 45 degrees. And we can also identify composition spaces that give us strengths of, say, 4 times that of the strongest materials that's used today. So what this basically means is that in some ways the glory has returned to Ashanti land, right? Because we can identify the best materials with this kind of approach in ways that we can use in all sorts of applications. We can identify compositions before other people do and test them in ways that can enable us to explore applications in medicine, in cars, in all sorts of applications, and discover materials in this way. We can also start looking at scrap. Next, please. And in the case of scrap, there are different scrap materials that we can mix together. And we can essentially work out the mixtures of different types of scrap that allow you to basically obtain different functional properties in ways that give value to recycling, in ways that give value to scrap, which essentially now puts us into a great domain to do material discovery, to create value from our waste in a way that can be strategic in how we do our research. And so with these examples, I hope that you can see that machine learning really offers us some great opportunities to give rise to work that can really make a difference. It can guide our experiments, it can guide our data collection and curation, it can guide how we predict things and what we invest in to achieve the goals that we want. And I believe that everybody here is another potential Chumesi. In my opinion, with all of us, what we have the opportunity to do is to use the machine learning opportunity as a way of leapfrogging into the 21st century and to begin to imagine a different Africa in which we look at the resources of Africa, next please, And those resources are many. In fact, if you look at the resources of Africa, Africa has 1/3 of the world's elements. 1/3 of the world's elements. There's no reason why Africa should be poor. If only we figure out how to create value, not just from the raw materials, but what we can do when we combine those guided by machine learning, guided by computational modeling, guided by evidence-based research, to make the best approaches. And we must also be inspired by the greatness of a man like Aliko Dangote, who is bold enough to say that I'm going to create factories to make cement, to process oil, to do these things on a grand scale that creates jobs. And it is my hope that within this group, especially amongst the young folks, that we have 100 Dangotes who can go out in all these different countries and turn these mineral resources into wealth, right? But let me inspire you a little bit. Don't just do it with the manufacturing techniques of today. Learn more about the new approaches to advanced manufacturing, with laser-based processing, with all sorts of bioprocessing and novel approaches. And think about how you can leverage your understanding of materials, of AI, into structures that don't have to start big. In fact, one of the biggest mistakes we make is to think that we have to start big. Most corporations start in people's garages. And as you do this, next please, what you will find is that, remember that you have the opportunity to think differently. Next please. And so as you look at this, recognize that in this era of AI, it's also the era of robotics. It's the era of using robots of different kinds to do manufacturing, where the human-robot interface matters, where as you think about logistics, think about robotics, think about how you bring this into practice in our own environment. As you think about construction, think about robotics and AI, because that human-robot interface is critical. And by the way, I challenge this group, especially young folks, to think about how we do agriculture in Africa. On the top left there is a robotic tractor. And that robotic tractor was designed by a guy called Kenemba Nisi. And he's engaged American students into a project where they're developing this robotic tractor for harvesting and for all sorts of functions. And you notice that it doesn't look like a regular tractor. In my mind, this way of doing things is going to disrupt the future, because connected to that robotic tractor can also be a processing plant and a packaging plant that can give value to things at the point of production in ways that we can create through projects that we do. And as we do these projects and as we explore the applications of AI at the interfaces, we should also think about companies in containers. The companies don't have to start big. You can take a container, and within that container, you start producing things at a small scale. And you can expand those containers in modular ways until you go from small to large. And so what I've tried to do in this talk, hopefully, is to show you how the next frontiers in AI are actually happening now. How through collaboration, we can build on what we have and really begin to define the solutions in problems of energy, in problems of health, and in problems of new material development. And the key to all of this, I say to you, is collaboration. It's collaboration identifying the sweet spots where we can make a difference and really look to what was imagined when KNUST was created. When Kwame Nkrumah created KNUST, the idea was to bring together this place that was going to create the technology for Ghana to industrialize. It was at the time when Ghana was ahead of South Korea, when Ghana was ahead of Taiwan. But they embraced that information technology that created their wealth at that time. What I do today is to urge you at this time in the fourth industrial revolution to engage the opportunity of AI and the Internet of Things and the Internet of Services by bringing together the collective ability that is here in a way that will make KNUST really a leader, a beacon and an anchor in a new era in which, just like the Asian tigers before us, we will look forward to an era in which KNUST will play the role of an anchor as we create the environment for a new generation of African lions. Thank you.
A round of applause for him. That's quite an insightful lecture. All right, thank you very much. So please, shall we have our seat? So Prof will be, your audience would like to interact with you. So we have about 15 minutes to do this interaction. And we have so many students here. So we have 15 minutes to do this interaction. So questions from the audience. I think some of the secondary school students have some questions. So I'm coming to you. Prempeh College. All right, we have one here. Great, so you mentioned your name and of course your school.
Okay, my name is Kusi Mensa Ramsfeld. Yeah, I'm in final year, Prempeh College. Okay. Okay, so my question, see, you spoke of being able to identify new forms of alloys using machine learning as in basis of also recycling. I wanted to ask, you see, as far as plastics are concerned, I believe at some point there are variants of plastics that have different heat capacities. I wanted to ask, is there a way, or is there even a database somewhere that can augment machine learning to identify different pieces of plastics and then sort them out in ways that would be available to industries for reprocessing? Thank you.
Thank you very much. Please give it to him again. Is that so well? So we'll take another question, then we go to our speaker. So another question. Come to the girls. So we have KNUST SHS here. You have St. Louis here. Okay. So St. Louis, who is going to do as the honors? Please. Any question? All right, so as we wait for the St. Louis students, we'll go to our students also to get some questions from our students. So our students, questions? Please, questions. All right, we have a gentleman here. You mention your name and your program.
Good afternoon. Thank you very much, Professor WOLE. Thank you for this opportunity. In his presentation, I heard him make mention of the fact that it is quite difficult, and in fact, we do not have the computational ability to process all the data we have in the database for alloys and different materials. But with AI and machine learning, it makes it more feasible to process all that data. And I am wondering, wouldn't that also require some computational power? So if there could be more clarity on that, I would appreciate it. Thank you very much.
All right, thank you very much. Since we have these two questions, we'll go straight to Prof. WOLE. You answer the questions for us as we wait for the other questions. Thank you very much.
Sure. Thank you very much for those insightful questions. So in the first one, there are plastic databases. And those plastic databases include the softening temperatures for different plastics, especially those of the thermoplastics. And with that kind of information, you can begin to figure out what are the temperatures you can reach in those plastics to recycle them into different types of products. You can also do things that are quite creative as you begin to process those plastics. So one of the things you can do, and you can try this out, is you take polyethylene bottles, you chop them up, and you dissolve them in some solvents. And if you heat them up a little bit, you can dissolve those plastics. And if you freeze cast them, they form little particulate plastics that are recyclable into building materials. So why do I say all this? What we need to begin to do is to begin to look at those databases that give you the data for different materials and begin to play with recycled plastics of different types, mix them up to form composites of different types, or even reprocess them into bottles in ways that allow you to give value to those materials. And you can also, just as I did for metals, start looking at databases in terms of what you can engineer with variations in the compositions of those materials. So your question is a great one, and I encourage you to pursue your materials instincts, because I think they will lead you somewhere that could create a lot of value. Now, the other question about computing is actually all this work that Jumesi has done has been done with a basic workstation. And it's not very different from much of what we have access to today. But I can assure you, with the Center of Excellence that you have here in artificial intelligence, if you have something that needs high-performance computing, really go see Professor Kwonyo. And I think you have the capacity to do a lot already here at KNUST. What's truly amazing, though, is the capacity of today's computers. Today's computers really are close to being supercomputers of yesterday. But you're lucky to be in an environment that has made an investment in having an AI center, where if you want to do some serious high-performance computing, go to them. And if that doesn't work, please reach out to us, and we will let you have access to our supercomputers. The problem actually today is not so much computing space, because you can do things by archiving data in the cloud and just using it as you need to. What you really want to do is to think critically about what are those important opportunities that I can pursue by doing this computation or doing this simulation, and then who do I need to collaborate with to have access to that infrastructure. So I hope this is helpful to you.
All right, Prof, thank you very much. So we take additional two questions. Two questions. Two questions. Yes, we have one here. Okay, we'll come to you. Okay.
Good afternoon. My name is Abdul Nasser Abdul Rashid Unam. I'm in first year and I'm offering metallurgical engineering. So my question is, if we are going to rely on AI and machine learning for computation in relation to data for alloys, does that not make the work of materials and metallurgical engineers redundant? Thank you.
Thank you very much. We'll go to the other question.
Thank you very much. My name is Godson Entry, and I'm pursuing aerospace engineering. My question is, could agentic AI evolve to make its own smart decisions about sustainability? Example, choosing the best way to recycle, reduce waste, and protecting the planet? And how close are we to building an AI that thinks long-term about the Earth's future?
Thank you very much. I think we have room for an additional question. So if I get one more question or two questions.
I am Kofi Kakari, Materials Engineering, Year 4. With the issue of your data cleaning, how sure are we that you don't actually create a model that is overfitting the data as in it performs so well, or it underfits the data as in it doesn't perform at all?
Thank you. A round of applause. So Prof will answer. Perhaps we have some time. We'll come to you again.
Okay. I guess the first question was about job security. Here's what I think. I honestly think that what we need to do is to embrace AI and become knowledgeable about AI. No matter what your discipline is, embrace AI. There is no replacement for fundamental understanding if it is applied creatively. So what's amazing is I look at the principles of material science and engineering that I learned 40 years ago, right? But it's informed with 40 years of experience of applying it in different contexts. And I can guarantee you that those new machines are not that smart yet. So what we should be thinking about is the interface between humans and AI, and how you can use this as a tool to inform the decisions that you make, to inform the things that you do. But there's absolutely no substitute for you. So I often look at people, I do projects with them of different types, and then some of them at some point will run away and do it themselves. So I'll say, okay, let them run and play, because they also deserve to do things themselves. But eventually, some of them will come back and say, let's play together again. And the reason is that your own evolution and knowledge and intuition as you develop is what sustains you over time. Where you have to be careful is to not fall into the trap that many people fall into in their careers. And I tell you what the trap is. So in the first phase of life, you do work, everybody appreciates you, and you can do the work. In the second phase of life, you supervise people doing work, and you start thinking you know everything. And in the third stage of life, you think you know so much, nobody wants to work with you anymore. And that's when they get you to retire. And those people often become threatened by the new knowledge that's coming. But what they need to do is to embrace that new knowledge and bring their experience to work with young people. So I assure you, AI is not the threat to your job. It's failure to embrace it and use it in ways that create value that are the threat to your job. Now I have to confess, I'm getting old. Please remind me, what was the second question? What was the second question? Oh.
Yeah, my question was, could agentic AI evolve to make its own smart decisions about sustainability? Example, choosing the best way to recycle. And how are we close to building AI that thinks long-term to protect the Earth's future? Yeah.
I think there's always a threat, of course, as AI evolves, that it could evolve into some states that threaten us. And so this idea of ethical AI is absolutely important. And I think one of the dangers we face today is we still haven't fully developed that framework. But one of the things that I find most encouraging about what is going here in rail is that at the center of it is the idea of an ethical approach to AI. There are boundaries, and those boundaries are such that if they do get exceeded, could result in challenges. So as you do this, I think one of the things I hope you always use to monitor yourself is the idea that it needs to be done within an ethical framework.
All right, Prof, thank you very much. The third question.
Go ahead.
For the third, with your data cleaning, I wanted to know if when cleaning the data, you sometimes omit certain entries. And I wanted to know if that might cause the model to either overfit or underfit the training you are trying to give it. So how do you come up to minimize such factors when you are building the algorithm?
Yeah, so there are certain encoding and appropriate imputation methods that we use to try to reduce those possibilities. And quite honestly, with overfitting, there are just many things that don't make sense that you get from the consistency checks that help you to manage those tendencies. And so this is an area where we work very closely with collaborators who specialize in these methods. And I could tell you some of those results, in fact, I would say all of those results that we got were informed by very judicious application of their insights to the processing and modeling efforts. So this is something where, you know, for example, when you're predicting efficiencies of 1,000%, you should be nervous, right? Because you know something is overfitting in a way that's affecting your data. And the pre-processing that was done and done with good judicious efforts is what enabled these kinds of results to be obtained. So my suggestion to you, especially in this area, is work in collaboration with people who have those instincts and insights to manage these possibilities. And always at the back of your mind, have a scientific framework that helps you to understand the results that you're getting. This, in my mind, is how you can truly manage things in a way that allows you to say, this doesn't make sense. This overfitting is giving me solutions that I know are not real. And also in cases where you have unbalanced data, you have to be very, very careful how you balance that data before you begin to make predictions with your models.
Prof. WOLE, thank you so much. In the absence of any question, there's a last one, Prof. Please forgive us.
Okay, so my name is Prince Tepe from Please, can I continue? Okay. So my name is Prince Tepe. I'm offering materials engineering. I've developed interest in artificial intelligence, and I would like to integrate it into my field of material science. But I have very little knowledge. So my question is, where do I start from? And then what can I also do to keep me going so that I don't lose hope easily? Thank you.
What was the last question? What can I also
Prof, please, let's take this question here
so
that I can answer. All right, gentlemen, your name?
Okay. Good afternoon. Please, I'm Raj. I'm studying materials engineering. My question is, with perovskites, right? We have lead-based perovskites. So for their recycling, if they are used in the solar cells and the solar cells run out of energy and you're about to recycle, wouldn't that be a problem to the environment? And why don't we rather look into dye-sensitized solar cells rather than the perovskite solar cells?
Bro, thank you very much. All right, Prof, please, you can answer.
So the answer to the first question about where do you look if you want to get involved in machine learning, you look here. So Professor Jerry, please get up. Don't let him go. So he heads the AI center here, and he will point you in the right direction. And not only that, he will connect you to people that can help you. And, okay. So the issue of lead that you talked about, so in my mind, you know, one of the things we know today is you can recycle lead. What we have to do is to think creatively about how we recycle lead and how we build this into a strategy. And so what this basically suggests is as we begin to think about all of the materials we use, the reason I talked about recycling is we need to always think about life within a circular economy in which there is no waste. And there are many applications of lead that require recycling. And so what we need to do is to build into the use of lead the recycling strategies that continue to create value. There are other perovskites that do not use lead, but the truth is the tin-based perovskites have other problems that have not yet been overcome. And I think that what we need to do is to plan for a world in which recycling is built into any extensive use of materials in a world in which there is no waste. So please, as you think about your project and you think about the environmental impacts, just always think about not just the application that you intend, but an environmentally friendly way that creates value from the waste. Thank you very much.
A round of applause for Professor WOLE.
We have one more question.
Soboyejo.
So I know you want to ask a question.
Yes. Say Louis.
Please, I'm Gabriela Sewainti, Form 2 student. I know this question might be out of the ordinary, but just curious. So, per my little knowledge in cancer, I know that laser surgery, radioactivity, gamma rays are those powerful enough to get rid of them. And then the physicians and the surgeons do their best to get rid of them. I was wondering whether there is any other safer and more accurate way to get rid of it, and then how it would be to, I don't know, to get to that cell, because sometimes the cell might be in a particular place that you may not see, that the machine may not see, and then sometimes it's difficult to direct that ray to get to that cell. So I was wondering if there were other safer and more accurate ways to get rid of them. Thank you.
Thank you, Gabriela.
Thank you very much.
So Gabriela, you know, I really appreciate your curiosity. And you've actually given me an opportunity to spend a little time to explain our strategy, because I didn't really fully explain why nanoparticles are important and why drugs are important. So most drugs, when you ingest them or inject them, go all over the body and cause all sorts of effects, but only a small fraction of those drugs actually get to the intended sites, right? And so when that happens, you get a lot of side effects of the drug, of the chemotherapy. And so as a result of these sort of toxic effects, the treatments are very severe, right? But the blood circulates them without you having to do anything and takes them all around the body. So with our targeted drug idea, what we find is if we conjugate onto that drug the molecular recognition unit that we found in African women, then what happens is we don't even have to do anything. The blood gets carried with the drug and takes it all over the body, but the drug only attaches to that region where the receptors are overexpressed. So essentially, it goes all over the body, but it finds its target because you have almost like a lock and key kind of connection to those receptors, right? So the key to a lot of what we do is to find out the receptors, and then once we find out those receptors, we conjugate them to the drugs, and those drugs, because they now deliver more specifically to that region, they can shrink and eliminate the tumor with less toxicity associated with them. And then you can go one step further and you can start taking nanoparticles, and then you conjugate them to those molecular recognition units, and those nanoparticles can go all over the blood, through the capillaries, through the blood vessels, and then they attach very specifically to those areas where the receptors are overexpressed. And when that happens, you can then do MRI to image them if they're magnetic nanoparticles. If they are gold nanoparticles, for example, you can shine a laser on them, and that laser will heat up that domain where the particles are to a temperature that's not very high, 43, 44 degrees, which will kill the tumor. And if you apply those lasers under different conditions, you can heat them up to the point where you can cut out the tumors with a laser scalpel. So the power of the nanotechnology aspect of this is significant, and the opportunity that AI offers to help us study those receptors also very important, because eventually we may be able to get to personalized targeting in ways that link all of these different pieces together. So the question you asked is a good one, and I encourage you to keep up your curiosity.
Thank you so much. So fortunately, the Prof Chair has given us a permission for 2 last questions.
All right. I'm Richmond Kofi Jr., a first-year metallurgical engineering student. And my question is about the energy crisis here in Africa. We know that energy crisis is one of the pressing problems here in Africa. And we know that aluminium, by research, shows that is the most abundant metal on our Earth's crust. And it can be used in the building of batteries. But here lies the case that it doesn't have a higher energy density as compared to maybe that of lithium. So my question is that, is there any way that we can modify aluminium to have, say, a bit similar energy density as compared to lithium, so that we can use them in the preparation of batteries that will be much more cost effective to reduce the energy crisis here in Africa?
Thank you. So the last question here.
Please, AC Kesson Beatrice from KNUST-TEK, and my question is, can you distinguish between artificial intelligence and machine learning?
All right, thank you very much, Prof.
So I think machine learning is often an iterative process that allows you to learn from prior cases better ways of describing a state. And in many ways, it can be guided, of course, by your understanding of appropriate statistical distributions that allow you to characterize the variabilities around that state. AI, I have to confess, is a bit of a sexy acronym. And today it's essentially been adopted to include almost all of the components of data science and how you manage data, process data, identify distributions, and use them to make decisions and apply in different contexts. And so I would say, at its best, it's the full description of all of those data science components in ways that you can apply to materials discovery, the control of machines, autonomy, and so many different applications. At the heart of it, you need to know a little bit of statistics, a little bit of especially some probability theory, and you need to be able to code to some level. And ultimately, you need to recognize that most things we look at can be considered as bits of information. So if you're thinking, for example, about sound, or if you're thinking about light, if you're thinking about imaging, you can consider them as bits of information that you can describe with numbers that allow you to use this as a tool that is now pervasive all across in almost every field. And so what I would do, for example, if I were any one of you, is no matter what your major is, take a course in AI. Even if it's very simple, just take it so you can internalize it and use it at the level that you want. And don't see it as a threat, right? See it as, wow, here's a chance for me to learn something cool, and I can begin to put it together myself in so many different areas where the knowledge of how to use this can create opportunity for me. Okay, I hope that is helpful.
Yes, and the last question about the difference between artificial intelligence and machine learning.
Between what?
Okay.
Oh, aluminium. And machine, no, the energy crisis.
Yeah. Okay.
So it's interesting the way you're looking at the energy crisis, and I want to reframe the energy problem a little different. So if I look at Africa, and I look at the energy sources we have in Africa, for example, if I think just geothermal, the region from Egypt down to Kenya, the strip there has enough geothermal resources for 1/3 of the continent's energy needs. If I look at the single drop of the Congo River, the single drop of the Congo River has enough energy for 1/3 of the continent's energy needs. If I look at the Sahara Desert has 1/3 of the continent's energy needs. None of it is harvested. Now, in addition to that, we have uranium. We have the Gulf of Guinea that has 10% of the world's oil and gas reserves. We have coal in South Africa, and we still have solar energy across the continent. So, in my mind, we do not have an energy crisis. We have a lack of application of ourselves to our energy resources problem. And what we need to do is we need the next generation to rethink how we're going to harness that energy, how we're going to store that energy, and how we're going to use it for many hundreds of years to come for future generations. Now, this issue about should we use aluminum, you have to forgive me because I know we say aluminum. I've been corrupted by America, so I say aluminum. But should we use aluminum or should we use lithium? I would put it to you slightly differently. What I would think about is I would think about those electrodes in the battery that you refer to. And I would think about the electrolytes. And I would say to myself, should I really use nickel, manganese, cobalt electrodes, or should I use carbon-based or lithium-based electrodes? And can I discover other electrodes that work better? Think more generally. No, don't be wedded to aluminum. Think more generally. Discover that space where the true solution will come from in a way that will allow you to invent that next battery, in a way that will allow you to think creatively, informed by the best data to identify the spaces of opportunity. And if you do come up with something creative, think about how you can make that happen through how you bring your knowledge and materials together to find that solution. So don't just be wedded to aluminum because it's some material that you learned about. Really look more openly at where those spaces are for those alloys that will give you the best performances. And then use your abilities in material science and engineering to really guide your path as you pursue that opportunity that might be represented by your idea. So I personally do not say we have a true energy crisis. I think we need to figure out how to harness the energies that we have and to do it in an environmentally responsible way. Thank you.
A round of applause for Professor WOLE. Soboyejo. Thank you so much, Prof. Drink deep or taste not the parents' spring, for little learning is dangerous. But we also know that lots of science and engineering come with lots of headache. And we need music. So Ajaku and our format, please take us away. Thank you very much. Ajako, Nimo, and Thank you so much for that beautiful music. So we go to the closing remarks and the presentation of souvenir to the speaker. And to do this is our Vice Chancellor, Professor Mrs. Rita Akusia-Dixon. Please shall welcome her again.
Thank you very much, Kwesi. What an afternoon we have had. It's been very, very educative, hasn't it? Can you help me do it for Professor one more time? It's impossible for me to try and summarize. I guess we've all been turned to engineers this afternoon. If you didn't become an engineer, you became an oncologist, specializing in cancer. If you didn't go on that trajectory, you became an expert in machine learning and artificial intelligence. He said something in his closing remarks, and I want you to take that with you. Imagine a new Africa. It always starts with a dream. It always starts with a vision. And as I look at all of you, students, I can just see the solutions to the continent of Africa in your heads. Yes. The professor whispered something to me as you asked your questions, and he answered and sat down. He said, Madam VC, the questions that the students are asking are very smart. In the morning, I told him that at KNUST, we have over 80,000 brilliant ideas and minds that we need to nurture.
And the pharmacy is this. And this saying that whatever it is, like pharmacology lab, biochemistry lab, all the 4 years of your stay in this country. I have the privilege and the honor this afternoon to announce to you that in this university we have a was responsible artificial intelligence lab in the College of Engineering. This is for Africa, specifically from Ghana. Is it he's also from Ghana. These are all Chinese names. More than I really calling to the Chinese names or American names, London names, so that tells you that you are capable. I want you to just do this and say, I love my people power values. And I can do this. And that's what on behalf of all of us, just to let you know that we really appreciate and we have learned a lot from this lecture. And we will continue to think through that. And as I look at the faces of all these students, I know that the conversation will continue. And as a university, we are going to continue to support them to be able to turn all these businesses into realities. So, thank you very much. And thank you. Join me, senior members, help me do this as we honor. I think that your team would want to join me. You want to join your president as we try and do some. Distinguished ladies and gentlemen, you know we are in the month of March. So Ghana, we got our independence on the 5th of March. So every March in the year we label it as the Ghana month. And what we are going to give to you today is very symbolic. Symbolic, and I think Prof is in one already. So this is a very rich attire that comes from the northern part of our dear country. And this one, you can get to use artificial intelligence to measure it's for the brain of physical human beings. And that reminds me of that security question. Because we want to be there to use the AI for which we work. So this one, we want to protect group of people. We can't let you take off the FRP, so we will get it all like this. And this is from the university to you. And this is to thank you very much.
And this desire to embrace artificial intelligence as a new frontiers and be able to use our genuinity to create solutions for our problems. As we depart from here, we commit ourselves to you. Grant any mercies to us. Lead us to our destination safely and sound. Bless us and our families. May we find joy and fulfillment in our various professions and career. For all of us who are present today, be with us, and may we forever be grateful to you. These are some blessings to our hearts, through Christ our Lord. Amen. Well, I'm very glad. So be very focused. So we now think about really how we have all of education for security rights. Your professional representative to classes so we can take it there. And as soon as we can take it and have a bit more professionals, and we're going to make it all right. Commander